You can build your own game engine, and it might be easier than you think. I set out to build an engine in a weekend, and if you follow along, you can end up with something like this. That is 3D rendering, physics, and audio. But before we answer the how, let's answer the why. Why would you bother making your own game engine when there's so many great options out there for you? I'm hoping a brief insight into why I spend my free time making game engines might prove illuminating. 1. It's a great way to learn how things actually work under the hood and provides a great appreciation for the heavy lifting engines do. 2. Having a large personal project is a great sandbox for testing out new ideas, tools, and language features. 3. It's fun. So what are we actually building? A game engine can be broken down into several core parts. Now, in a weekend, you won't have enough time to build all these from scratch, but you can take open source implementations for all these and smash them together at high speeds to build an engine. This may not sound like you're making an engine, but 1, yes you are, and 2, by using these building blocks, you get to focus on what I think is the more interesting problem of how do you actually engineer a system that allows all these disparate bits of code to work seamlessly together and provide a coherent user interface for people to use. In addition to that, so I guess point 3, as you develop your engine API and start to expose more of the functionality from these low-level libraries, you'll start to think about how you would do it yourself from scratch, and then you can start looking at replacing these open source projects with your own implementation. So what are the projects that we're going to Frankenstein together?
It's alive! It's alive! It's alive!
For graphics we have Ogre, which was the original rendering engine for Roblox before they replaced it with a custom one. For physics we have Bullet, which was used as part of the Rage engine for GTA 4. And for audio we will use SDL, which has a long list of usages, including the source engine. The key thing here is that all these projects have been used as building blocks for commercial engines. So if it's good enough for Valve, it's good enough for us. So let's get into it. Step 0. Name. Obviously the most important part of the project is the name, so feel free to pick whatever you want, but preferably not an existing engine. Classic suggestions are your pet's name, random word generator, random word generator into Google Latin Translate, 16th century French phrases that were first used in Victorian Britain. The reason I like bric-a-brac is not only is the meaning apt, a selection of items with modest value, it also abbreviates well, so I can just use BAB throughout my code. Now that we've settled on BAB, it's time for step 1, setup. For this I will be using C++. If you want to use another language that's fine, but for each of our projects you'll have to either check if it has bindings for your language, write bindings for your language, or find a different project. In terms of environment and tools, I'll be using VS Code and the native compiler for each platform. So for Windows that's MSVC, for Linux that's GCC, and for Apple it's Apple Clang via Xcode. I'll include some instructions for setting these up on Git, but you want to make sure that you can compile C++ on your chosen platform. For the build system I'll be using CMake. This has 2 advantages. 1, it's integrated into VS Code so it's easy to set up and use cross-platform. And 2, CMake has a built-in function called fetch content declare, which allows you to check out a Git repo, and if it's a CMake project, makes it easy to integrate. Step 2, lash together a sample program. So you've got a development environment set up with C++ and CMake, so you're ready to go, right? Well, let's rewind a few seconds. Makes it easy to integrate. Makes it easy to integrate. This simple statement glosses over the fact that CMake is a complex beast, and not all CMake projects are made the same. In all honesty, you could spend a whole weekend just trying to get these projects to build together. Fear not, for I've got you covered. If you just want to jump into making an engine, then you can check out the one I built for this video. Then check out this tag, and you have a project all set up with CMake which pulls in all the relevant libraries and makes sure they're all built together. Some features of this are, it builds the engine as a library and has a sample project which uses that library. All the code is in one horrendous blob in one function called entry, so it's ripe for ripping apart and rebuilding. Of course, if you want to do this by yourself, then you can. Feel free to look at what I've done for inspiration, as the comments explain some of the edge cases. At the end of the day, you want something that you can start building an abstraction over and produces something visible. Step 3, abstraction. Now we can get to the meat of the project. The goal of abstraction is to provide a nice interface that your users can program against whilst hiding all the complexity. So for instance, instead of making direct calls to Bullet to create a collision state, set its initial inertia, create a rigid body, set its friction, and then add it to the simulation, we want the user to just be able to call add rigid body with some easy to understand arguments. The first thing I did was pull out all the primitives I would need and would want to expose to the user. Let's look at vector 3 first, which represents a point in 3D space. That is an X, Y, and Z component. Ogre has its own implementation, as well as Bullet. So you have several options here. Write your own separate implementation from scratch, bring in a dedicated maths library like GLM, or pick one of the types you already have and use it across the code. I picked the latter option. I aliased ogre vector3 to my own type in my own namespace and just used that across the code. When I needed to pass it to bullet, I just converted it internally. I did this for quaternion, colour, degree, and radian. Next was to wholesale shift all the ogre windowing code out. I created a graphics manager class which handled the setup, teardown, input handling, and exposed a single public method called start rendering. This allowed me to remove all this code and replace it with this. The entry function is still building its pre-made scene, so I extended the graphics manager to create planes, cubes, skyboxes, lights, and meshes. This allows the user to build whatever scene they want. Finally, I allowed the user to register custom callbacks for when the frame starts and ends. This allows you to create an update loop. For physics, I did the same thing. I moved all the setup and teardown logic into a physics manager class and added methods so that a user can create their own rigid bodies. However, now we have a problem. The graphics manager needs to know about the physics manager, so it knows where to render its objects, and the physics manager needs to know about the graphics manager so it can render a debug layer. As the saying goes, we can solve any problem by adding an extra layer of indirection. So I created the scene manager class, which is constructed with both the graphics and the physics manager. This handles setting up the debug drawer, as well as synchronizes the position and orientation of the physics and graphics entities. There's a few smaller classes I added to wrap things like bullet rigid bodies and ogre scene nodes, but it's all documented if you're interested in the specifics. Finally, I added callbacks for the collisions and an audio manager so we can play sounds when the boxes hit the floor. Now our sample program doesn't need to call this one big entry function, it can build the scene it wants from the primitives we supply. Now I'd be lying if I said this could go toe-to-toe with something like Unity. However, the beauty of writing a games engine is that it's a project that never ends, there's always more to do. As a starting point, here are some things that can be improved. The camera is static, so can't be moved around, which is somewhat limiting to gameplay. Only cubes can be moved after they are created. Lights are all static and cannot be moved. The physics only supports cube collision shapes, but Bullet has a rich range of possible shapes. So what have we done? We've taken a range of complex open source projects and built them all together. We then created a simplified abstraction over the top of all of these, which allows a user to easily interact with all of them. Sounds a lot like a game engine to me. I hope you enjoyed this video and the project idea. I've uploaded what I've done to GitHub, and you can check out the commit history if you want to see the steps that I took. If this was useful, then consider subscribing. But if you want to see how I added water to my own custom game engine, then check out this next video.